All right, so I think we're all on the same page now. We're in Desmos. This is your code, UWXSE5. And you are restricted only up through page 4. So give me a real good definition. I want like the best response you can create for what you think it means to be scale, or what it means to be not scale. So work your way up through slide 4, chat about those, and then we will keep going. Again, this is something I have never tried before because it did not exist last year. So please bear with me as we stumble our way through this. So it was this, or we do the standard lesson involving like some drawing of stuff on graph paper, and I kind of thought you would like enlarging Dan into a giant a little bit. Now, the part of this that is like inside story Dan is actually the CMO, I think is Chief Mathematics Officer at Desmos. His name's Dr. Meyer, actually, he's Dan Meyer. But I bet he made this, and that's why he called the first guy Dan. And he literally says words like hi. What's up, Mr. Estes?
I want to ask George a question.
Mr. S is hi.
You have my
Science.
and in between is the science. Probably someone just did earlier.
So some of these answers with a scale, nothing changes except for size, each individual shape, line, etc. change the exact same way that everything else does. That's a pretty solid definition right there. Or Caroline series is. Carl Weierstrass. A scale is when Dan has the same proportions. There's a math word. And is a different size. Not scale is still being typed, I believe. The not scale has different faces and swords that are not, if you scale the swords down, they will not match. But the scale Dans are the same face, body, sword. If you make them smaller by times X, they will be the same size. I like that one a lot. A scale of Dan is when it's an exact copy, but dilated, another math word. Not scale is when something other than scale. I like when you define something by saying something other. Not scale is, not scale. With scale drawing, nothing changes except for its size. Scale means that the size increases or decreases but stays in proportion. Florence Nightingale, that's a very nice definition. Scale is bigger or smaller proportions of the different, or of the original Dan. Not scale is different proportions. I like it. Should I unrestrict you? Should I let you move on to 5? I think what makes a giant scale of Dan is when you multiply the original numbers in order to get a dilated shape of the original shape. What do we call the original, actually? What did we call it last week? The pre-image, right? The original is our pre-image. The scale of Dan is an even stretch of an object on all axes. What makes the other not scale is because the scales of him have elements of him moved around in the first. They would all be the same if they were scaled down to the same size. And the not scale would not be even if they were scaled down to the same size. I like it. All right, I'm going to undo my pacing and let you guys move on. So the next task is building Marcellus. I like your scale definitions, guys. Ooh, here we go. Same pre-image. Now be careful, this should be dilated to a bigger Dan. Ooh, perfectly enlarge or decrease it. It's just a dilated image. So now, I don't mind if you guys chat with each other, but there's not one right answer. It depends on how you decide to build your Marcellus. So be careful. Like, you might not be doing the same thing as a partner. I also thought that this guy looked funny, so considering I laughed when I pulled this activity up, I was like, yeah, we should do it. Yeah, you're choosing what scale to use. You can use fractions, you can use negatives, you can get as creative as you want. Gwendolyn made Dan tiny. I think Teak has melted Dan somehow. What are you doing? You're gonna go to like a million. That's gonna be your scale. I'm just gonna scale that up a bit. We'll take it to 110. Now I thought we wanted to make Marcellus a giant.
No, Marcellus can be the smallest.
So a couple of us are playing with negative numbers. Yeah. Now, technically, you can't have a negative scale factor, but mathematically, you can go ahead and plug one in and play with that and see what happens. It flips it, right? It reflects it. All right, so I get that that one's fun, but move on from 5 to where you actually have to make Marcellus. So you want to drag the different features to try to make it look correct. Some really funny activities up here. I'm sorry, but if you can look at this and not laugh. I don't know who Gene Taylor is. So if you multiply by a negative, Dan flips over. I don't know. His sword's right side up.
Oh, yeah.
Your goal in the next 30 minutes is to process all the way through the end of this activity. Okay, there are 15 slides in total. When you are successfully at slide 15, you can show me your computer, and you may work on this. So make sure you process through this, because this is discovery learning. I do not want you to hear me say that and just think, oh, I need to get done as fast as possible. Click and drag. Mouse might be easier. Are you supposed to move the mouse? No, wait. That's Dan. It says make Marcellus scale to Dan. So you're not moving Dan, you're moving Marcellus. Are you able to zoom out on that? Or like reload the page after this? Yeah. So like I said, I've never done this before. We're gonna figure out these issues.
back to where you choose your scale. What scale did you choose? Yeah. Yeah. See, you're just not playing by the rules, George. Troublemaker. So you are adjusting Marcellus. Can you drag one of those points? So wait. You have a response type, yeah. So wait. If Marcellus is 4 times as big, and Dan's eyes are 5 units apart, how far should Marcellus's eyes be apart from each other? Dan? There. Okay, some of you that are having issues, just gotta read the instructions. Play by the rules.
Nice.
So I'll read these instructions. So change the slope of the orange line. Drag the points on the graph to locations that aren't on the orange line. What do you predict your new giant will look like based off where you place things? So where you place your points is going to determine what your prediction is.
Someone's making Marcellus 250 times Dan. That's kind of big. Okay, Gene Taylor. Let's calm it down.
I made an alien. I somehow made an alien. I'm 12.
So like I said, your work may be different than the others. This is where everyone's is going to be unique. Right? So depending on how you change your orange line and where you put your points, it's like Galois here is a scale model that is much smaller than the original. So if I look at this one, right, and I drag this to like 2020, what would it mean that this line hits like 1010, 2020, 3030, 4040? Like, what does that actually mean about the giant compared to Dan? Braylon? Ignore the black points right now. If we just compare how a Dan dimension compares to our giant dimension, if they're the same, what would that mean? Yeah, they'd be the same size, right? So the giant, quote unquote, would be the same as Dan. If I drop this orange point to where Dan is 20 and the giant is now 10, what does that mean? 20 compared to 10? Yeah, the giant's smaller, or Dan is 2 times as big. And likewise, if I put this point up here to 20 compared to 10, now the giant is 2 times as tall as Dan. So depending on this slope of this line, that's really going to change how stuff looks. The more vertical I get, the bigger the giant is compared to Dan, right? The more horizontal I get, Dan is bigger compared to the giant.
Oh, that's weird. If you do the line perfectly, he's off the map.
Like the 2020?
No, but like if you do it the y-axis or x-axis.
Oh, yeah, like this, he'd be too big. Yeah, he's like infinitely large then. If we're on the axis, we technically can't use that line because the y is quote-unquote infinity when the x is 0. Right, so we know that this point exists, but we can't talk about the line like that. That actually is not a function, which we'll learn about that later.
Wait, well, how do you go past the y-axis?
Like this.
Yeah.
So Dan's dimension now is some negative number, which doesn't realistically make sense, and the giant is still some positive number.
Yeah, but maybe the giant, the new guy is upside down.
Yeah. So it's just forcing it to work. It doesn't realistically make sense. So if we're talking realistic scale factors, they gotta be positive, right? But we can mathematically use negatives if we want to. Really quickly, hands off keyboard, give me your attention for just a second. Here's what we were gonna run through for the lesson. Braden, real quick, what's up? Is that it? Oh, you're just hands up. Oh, I thought you had a question. So, also, I wanted to save paper. If we looked at comparing which shapes are similar, we talked last week about similar shapes don't have to be the same size. They can be, what's that word we use to change the size only? Dilated, right? So we were going to compare on this sheet which ones are similar, and we can do that by checking angle measures. So if we cut these out and try to line up like this angle down at this corner for F, and or this corner with that corner, or this corner with, if it all lines up and all the angles are the same size, it should be the same shape, just dilated, right? So that was going to be one thing that we do. We were going to talk about scale factor, which we've already talked about last week, and we will continue to talk about it. What does it mean when shapes are congruent? Not similar, but congruent. This is why we're going over this. Make a mental note, make a real note, whatever you need. Congruent means absolutely the same. Same size, same, it could be oriented differently, but the shape itself has to be identical. Okay, not pointing the same way, but congruent means two shapes are absolutely the same, which means if they're absolutely the same, that's a scale factor of 1, right? Because multiplying by 1 does not matter. So if on an assessment, hint, hint, nudge, nudge, you were asked, what does a scale factor of 1 do to a shape? What does a scale factor of 1/2 do to a shape? What does a scale factor of 2 do to, like, you'd want to be able to talk about, well, 1 shrinks it, 1 makes it bigger. 1, literally the number 1, does nothing. We were going to do this, talk about how it was similar, and this was all the stuff I was talking about having to draw. This is the only other thing, so still give me your eyes, please. When we use fractional scale factors, we just take every dimension we have and multiply by that fraction. So for applying a scale factor of 5/3, easiest way to do that, divide by 3 first, then multiply by 5, just because how the numbers work here. So if we had a 12 by 12 triangle, a scale factor of 5/3, we know it's going to get bigger, but what's it going to actually end up with? Well, 12 divided by 3, 4, and multiply it by 5, what would we get? 20. So our new dimensions would be a 20 by 20. And we were going to do that on graph paper, but I figured Dan and Giant Marcella is more fun. Yes?
So, like, so when you're doing that method with fractions, you have to do the denominator first.
No, but it's easier. I mean, you could do 12 times 5 and then divide that by 3. It's just how big of numbers you want to deal with. That's it. That's pretty much it. So we're just going to continue working through Marcella the Giant, and once you're done, you may work on practice work, which a lot of us are getting close to that done point. And then I'm going to show you guys, I'm going to pause my video because I need to mute my screen and stuff. I'm going to show you guys that whole thing I got in a fight online about. That math video. I fought some people about math.